So phospholipids make up the barrier and allow for the concentration to stay low in the cell or low on the outside and allow things to move in and out. Cholesterol adds to the viscous, or makes the cell membrane more viscous. Glycoproteins and glycolipids deal with cell-to-cell reception. This is an example of simple diffusion and passive transport, the movement of molecules from an area of high concentration to an area of low concentration. So these dimolecules are moving from the outside of the cell where there's higher concentration to the inside of the cell where there's lower concentration. So with facilitated diffusion, you have an aquaporin channel protein, which is a channel protein that allows water molecules to pass through the channel by means of facilitated diffusion. So the energy pushes the water molecules through the channel and into the cell. With a monosaccharide carrier protein, the shape of the protein changes to allow molecules to come in and out of the plasma membrane, so it opens up to allow the circular molecules to come through and in. And then with a ligated ion channel, a channel protein that opens to allow ions, such as Ca2+, to enter the plasma membrane when a ligand attaches to the protein. So a ligand attaches to one of these molecules and moves it through the channel. With protein pumps and active transport, you have the sodium-potassium pump, which is 3 sodium ions bind to the protein channel, and ATP energy changes the shape of the channel and drives the ions through it. The sodium ions are released on the outside of the membrane outside the cell. The new shape of the channel has a high affinity for potassium ions, and 2 bind to the channel. This binding causes a change in the shape of the channel, and the channel releases a phosphate group on the cytoplasm side. This brings the channel back to its original shape, thus releasing potassium ions into the cell. The new shape has an affinity for sodium ions and starts the cycle all over again. Both potassium and sodium ions are moving against the concentration gradient, so low to high. And then, so the proton pump in a electrogenic pump is the proton pump found in plants, fungi, and bacteria on membrane proteins that store energy by generating voltage across membranes. The proton pump uses ATP for power to translocate positive charges in the forms of hydrogen ions. The H+ concentration, or concentration gradient, and the voltage represent a dual source of energy that can drive other proteins like the uptake, or drive other processes like the uptake of nutrients. And then co-transport, so sucrose and H+ co-transporter, both hydrogen ions and sucrose molecules are able to use the co-transporter to pass from outside the membrane into the cell. They have to pass through the co-transporter together. The proton pump ensures that there will be enough of each molecule to pair up and pass through the transporter. So the proton pump with ATP makes sure there's enough hydrogen to join with sucrose to pass through the co-transporter together. So exocytosis happens when the Golgi apparatus produces proteins and molecules that's transported into vesicles and then brought through a pocket in the cell membrane, and then the proteins are secreted to the outside of the cell. Penocytosis, pinocytosis, occurs, it's a mode of endocytosis in which small particles are brought into the cell, forming a small pocket where the particles are then transferred into vesicles. These vesicles fuse with lysosomes to hydrolyze particles. The process requires ATP. Pinocytosis is used primarily for the absorption of extracellular fluids. And it differs from phagocytosis, which is a process in which a cell engulfs a solid particle to form an internal vacuole called a phagosome. Phagocytosis is a form of endocytosis involving the vascular internalization of solids, like bacteria, making it unique from other forms of endocytosis, which involve liquids. In multicellular organisms, the process eliminates debris and pathogens. In sickle cell organisms, it is homologous to eating. So receptor-mediated endocytosis is when the plasma membrane takes in hormones and proteins through endocytosis, in which pockets are formed. Vesicles then take these pockets with proteins to the Golgi apparatus. So for 4 of the questions. So, starting with question 3, how does each component relate to the selective permeability of the cell? So with the phospholipids, they make sure that so that the concentration stays the same inside and outside the cell, and allow the different molecules to pass through. And then the transmembrane proteins are the actual channels and pieces that make it so that these individual molecules can go into the cell. And then so with question 4, it describes specifically how the phospholipid bilayer is a barrier to polar molecules. These heads on the phospholipids are hydrophilic, meaning they like water. And polar molecules don't like to cross with the hydrophilic heads. making things that are polar have a hard time getting into the cell. The specific function, so for question 6, what is the specific function of each of the basic structures that comprise the cell membrane? So phospholipids, we already talked about how they relate to the selective permeability of the cell, make sure certain things can't pass through. Cholesterol deals with making the cell, the plasma membrane more viscous, which also deals with letting things in and out. Glycoproteins and glycolipids are what does cell-to-cell recepting, so it connects to the same type of cells. And then with question 2, compare the differences between the structures and functions of the proteins used in facilitated diffusion of water and monosaccharides. So with water, it's simply a channel that uses a little bit of facilitated diffusion to pass the water molecules through with energy. And then when you're dealing with a monosaccharide carrier protein, the shape of the protein actually changes to allow the molecules to go through. And then the last question is question 1. What are the basic differences between active transport and passive transport gradients, as well as electrochemical gradients, and what evolutionary mechanisms at the membrane level assist the cell what it needs regardless of the gradients? So with active transport, you actually need ATP energy to force the molecules through the channel into the cell, but with passive transport, you don't need any energy, it just flows through on its own. And the evolutionary mechanisms at the membrane level are actually the plasma proteins that either are used with active transport, like the sodium-potassium pump, or the electrogenetic pump, and then those that are not, like just simple diffusion through the cell membrane.